Good afternoon, or I should probably say already good evening. Thanks very much for coming to this, I think, last session on this track for today. I know you've probably have had a lot of input on the last 3 or 4 days, and I know I appreciate it that you still come. Now, I try to make this kind of easy to digest for you. So I don't think this is going to be the most challenging talk that you're going to listen to, that you're going to have in the last couple of days. So yeah, as the title said, it's going to be about distributed systems and various ways how to implement and handle distributed systems. We're going to look at frameworks, Kubernetes, service meshes, and the eBPF technology. Now, a few words about myself. I work for a consulting company in Germany. We're about 300 employees, where I do mostly consulting in the cloud-native space. That means like both dev topics and also platform topics. What most people probably don't know is I'm also a teacher at 2 universities in the area of Stuttgart, where I teach the subject of distributed computing or distributed systems. And distributed systems sounds a bit like an already ancient term, so to say. So what I really try to do there is to do distributed systems with kind of modern technologies to make that attractive for the students and also still teach them things that they should know. And here is a kind of a chart or a diagram with some of these technologies that I would say are modern technologies to implement those patterns. This is basically the things we're gonna look at. I created the initial version for this talk for the Spring I/O conference in Barcelona this year. But as this is not like a plain Spring conference and it's wider in the Java space, so I'm also going to add some further aspects of Micronaut, Quarkus, or maybe Java in general. Whereas I should say the majority of my background or experience is definitely on the Spring side. All right. So as a quick agenda, of course, I'm a big fan of starting with why. Like, why would people actually do distributed systems? What kind of benefits do you think you're going to get? And then how are the options to implement that? What do you need to do? What does it take? And this is what we're going to basically elaborate on the 4 different options. And then basically wrap it up. Maybe I can show a few things live. The 50 minutes should probably be okay for that. All right, so yeah, we're going to start simple. I know, as I said, it's late. I don't want to stress you. A couple of ideas of like why would people distribute their systems, or basically to say why would you split one problem into many problems? In which way would it make your life easier, or when would you probably not do that? Now, a couple of obvious reasons are on the side of heterogeneity, so that you basically have different things that your overall system does. And when I mean this overall system, I also want to put this into relation to like the consumers, the clients. They would either access it over a UI or an API. It should still appear as one system, right? Internally, you have the distribution. You might want to run different tasks that could do different things in parallel to basically optimize things. Or you could also have like a heterogeneous landscape in terms of operating systems, like mainframe, Unix, Linux, Mac, whatsoever. Or some form that we probably see very often nowadays also goes a bit in the direction maybe of like polyglot microservices, that you have various frameworks for various jobs and basically go into the direction to try to take the right tool for a certain job and put your systems together in that way. If we narrow it down furthermore, it doesn't really have to be such like a huge polyglot environment. It could also just be like individual versions that differ, but still you would have different runtimes to get all your things together. And finally, on that aspect is also, of course, if you want your system to grow over time. So basically, if you want to add new components without the necessity to restart everything, then extensibility is certainly also a factor. Stepping a bit away from that heterogeneous part, it's also the availability, or I should say resilience part. So a lot of people do implement distributed systems because they want to provide a better experience to their end users in terms of availability and robustness of their system. So if you have 4 instances of a certain application, one goes down, it shouldn't really matter because the client should still be getting the access to the live ones. And another, like in that context, is also the terms of load balancing. So if your clients increases, and this is like a thing, I think with cloud-based applications, or that's something you want to be probably prepared for, then you're able to scale out and distribute the traffic across those systems. On the other side, if they're getting too many requests, either by sudden popularity, but also by malicious attacks, you might want to also have something in your environment that stops or that prevents the system from collapse. So things like circuit breakers or bulkheads, where you say, okay, we're getting too many requests now, and before everything goes down, we rather block the system for a while, maybe spin up additional instances, but basically with the overall goal to have the things healthy, and rather have a controlled mini outage as like a real big bang where things break together. A subform of that is like the rate limiting, where you say, well, I will throttle the traffic a little bit, and then once I have more instances, I can extend it again. Security is, of course, also a factor. Not every request that comes into a system is allowed to get into the system, so you might want to have components to filter that out or to block that. And then on the terms of updates, it's also an efficient pattern to say, well, we do something like blue-green deployments, or A/B testing is sometimes referred to, where you basically deploy a new version in the same environment where the other one is already running, and then basically switch the traffic. So in the end, you can enable new functionality without the client noticing that you actually updated it. So keep the clients happy that way. A special form of that is the so-called canary release or percentage routing, where you say, I don't want to switch the traffic entirely. I might want to do this gradually. So I might only going to roll out a certain percentage, and if things go bad, it's not so super bad because not everyone is affected and we can still roll things back. Another version of that might also be to like some opt-in mechanisms, or for example, if you go to a web page and they say they have a new version of that. I recently had that with Google News, and say, okay, I want to try that. Then a cookie will get set, and based on that traffic information, you will be either routed to the new or the old version. So there are many different things you can do there. Now, there are probably more, but I'll leave it with that. And if you want to do that, I mean, if you want to build systems like that, it's like, what does your whatever tooling have to provide in order to get there? I mean, this is pretty obvious. It's a distributed system. Things need to communicate. So I guess I can skip that. But more important is that kind of a routing, traffic shaping, whatever network component. And you might have that in various flavors, because that's really the piece that would either route, distribute, throttle, or even block your traffic, and the way to place that in the environment. Another thing which is also very important if you get more and more different parts of your system is something like a telephone book, like a service registry, where new services, when they join, will say, hello, I'm there, you can find me under this telephone number, and other services can basically query it then. So as the nature is pretty dynamic, of course, they cannot start and already know about whatever is out there at the time. Then distributed configuration, of course, as well. If you have some changes in your config, most likely this will not affect only one component, either several ones or all of them, and you need to have some kind of mechanisms to make sure more of them are going to be addressed. And we heard a lot about logging and tracing in the last couple of days. This, of course, gets more complex as well if your environment is distributed. Now, these are the challenges. These are the things you basically need to achieve to get a sample system like that. So I just sketched one out where I have like kind of an API gateway in the front and then 4 services. And you can see that only with 4 services and the service registry configuration and then some observability tooling, things can already start getting fairly complex. And it doesn't get less once that continues. But if you do that right, then in the end, you will get all those functionalities, like I roll out a new version of service A, or I basically scale out service D and service C load balances across them. Then you can basically do all those things. Now, if we go back in time a little bit, one company that had those distributed challenges was Netflix. They pretty early went into like a microservice and distributed applications direction, leaving them a monolithic architecture. And for that, they had basically the same problems. So what they did, they wrote in an open source package, the Netflix OSS, with various implementations for service registry, configuration, load balancing, and resilience. So I'm not going to read through all those names, but they started with that. And if we look back at this traffic component, this will basically show up here in various forms. So on the API gateway, you basically have a routing component. On the client, you have like a distribution or a load balancing component. And with Hystrix, you have like a circuit breaker where you can block and throttle the traffic. So you can basically say, where in your application do you need that functionality and place it there. Now, this approach was basically continued by Spring Cloud. This is basically also, I think, the first contact point for me. Some of the projects kept their name, some of them were extended. I don't know exactly what that relation was. But the same aspect applied, that you could say, well, I decide myself where I need it and where I don't need it. The way those things got implemented, in this case, for example, the service registry, it's like you would add a dependency to your application and then activate it somehow in code, very often through annotations. Other things like a service client would have a combination of dependencies, a code annotation, and some external configuration. Either way, it definitely meant that you need to add something on your code bases to activate that and require kind of a rebuild and a repackaging. So one more example, this is like from the Spring Cloud Gateway, how you would define a routing mechanism. So you would add the dependency here, and then in the configuration, you could specify if some request comes in here, please route it down. Now, looking at the overall picture here, if you want to do that, this approach gives you one big advantage because it's totally independent of the underlying framework or runtime or architecture, whatever, or infrastructure. That's probably the right way. Because it runs as processes, and that could mean all those processes run on one machine, or it could mean they run all on different machines, or they could run on containers whatsoever. So as the functionality is built into the code, it will always work that way. But on the downside of things, it would always kind of require a rebuild and a repackaging. Now, stepping away a bit from Spring Cloud and looking more into Micronaut and Quarkus, and again, as a disclaimer, I hope those things are all correct. My experience with that is limited compared to Spring. Micronaut does not come up with an own kind of library to address those things. What you can do with Micronaut, you have configuration options or starters where you can basically pull in the Netflix OSS libraries, or you can use HashiCorp console for service registry and configuration, or things like resilience for J as circuit breaker or other resilience mechanisms. With Quarkus, if you browse all the options that you have when building your application, you will stumble over a set of libraries or implementations called SmallRye. This initially comes, I hope I do this justice, from MicroProfile side. It's also adopted by OpenLiberty and Wildfly. So it's basically a generic set of implementations which can be used by different frameworks. I don't want to go through all of the functions and functionalities in there. But in general, you have things for external configuration, service discovery, fault tolerance, and so on. So you kind of, but also most of them, or some of them, when I checked it last time, are not in a very mature state yet. So some of the things are still being described in a beta version. But they are there. So you can basically do that with every framework of your choice and basically are able to build up such an implementation. To summarize that, things happen here on an application level, mostly in a combination of dependencies, configuration, and code. And it gives you total transparency of basically where the things run. And also the advantage that you can say, well, I know I only need a circuit breaker here and I only need load balancing there. So you don't have to like over-engineer your application. Now, one of the reasons, probably, and this is my assumption, and I don't have any written confirmation that why this functionality doesn't have such a footprint on Micronaut or Quarkus side is most likely that the Netflix OSS and Spring Cloud actually have been developed before Kubernetes entered the stage. And when Micronaut and Quarkus came out, and particularly Quarkus claims to be like Kubernetes focused or OpenShift focused, but the underlying thing is the same. So they're already built in a way that they would expect to be run there and take the advantages of that platform. Now, if we look at Kubernetes, and I won't be able to give you an introduction into Kubernetes, but on a very high level, it's basically you run things in containers, and you have another wrapper around these containers, which are called pods. You have many, many more objects, unfortunately, way too many. But this is basically for a fundamental introduction. Now, Kubernetes comes out of the box with own API objects, like a deployment, a service, a replica set, config map, secrets, and so on. So a lot of those components fulfill exactly the same requirements as we have seen before. And the idea of Kubernetes is, of course, then to say, well, you don't need to build it into your application. We provide that out of the box for you. And you can basically do that with any language of your choice then, because it's completely agnostic to what it comes in terms of programming languages. So some examples, for example, I guess most people have worked with Kubernetes, like a Kubernetes service fulfills two different purposes. On the one side, it registers itself in the Kubernetes service registry with a certain name, so it can be then looked up and found by all the others. On the other side, it also does kind of load balancing between the available instances of pods, which basically match the services. So they are going to be collected via labels. So they get a name right here. And if you have many replicas of that name, then the service would basically distribute the load. So we have service registry, discovery, replication, load balancing already out of the box. We have more things for external configuration, where you can use config maps and secrets to put like an external way of configuring the applications that run in your system. Now, what do you do if you basically have started with something like Spring Cloud, and then suddenly Kubernetes is there, and you might want to leverage Kubernetes and migrate your stuff there? Of course, it's pretty obvious you won't need two different service registries. That would probably be more problematic than helpful. And for that, the Spring Cloud team has basically extended the Spring Cloud package to something called Spring Cloud Kubernetes, where you can basically exchange the dependencies, but leave the code as it is. So you can basically still act from a client perspective as you would talk to Eureka, but you're actually using the service registry of Kubernetes in the same way. Same goes for config maps and secrets. So you can use that with the same configuration property annotation as you would do that without Kubernetes. All right, so if we summarize what Kubernetes does, you see it provides quite a bit out-of-the-box functionality for a lot of those things: scaling, load balancing, service registry, external configuration, and a few more. However, what it kind of lacks is the ability to react on things on the network. So there are no built-in resilience patterns in Kubernetes where Kubernetes would start blocking some traffic or throttling some traffic or whatsoever. You cannot tell it if certain things happen, then route this traffic this way or route it that way. So in that kind of aspect, at least the out-of-the-box vanilla Kubernetes is not equivalent to that. In order to basically bridge that gap, there is a technology called service meshes. So how that works, I told you before, the applications in Kubernetes are running in another wrapper around the container layer, which is called a pod. And basically, a pod normally contains a container and is somehow connected to the Kubernetes network traffic. Now, a pod can also hold more than one containers. And the important aspect of that is that multiple containers in one pod will share the same network address. That basically means all the traffic that one container will see is what the other one will see as well. So very often it doesn't make much sense to put two application pieces of containers in one pod. But where it might make sense is to use that functionality for something like proxying or agent behavior. So one is the application, and the other one basically listens on the traffic and then can maybe be helpful in that. That's the underlying concept of a service mesh. And it becomes more helpful if you expand it to a bigger picture and say, okay, I'm not going to inject this proxy into one, but I'm going to inject this proxy into everyone. Because then I suddenly have information of the entire network flow in my cluster. And then I can summarize that and aggregate it and basically take certain actions upon that information. So the side of the collection is actually called the data plane, and the part where the action happens is the so-called control plane. Now, this brings, of course, another advantage. You can now build such resilience patterns and things in there pretty independent of the framework you use. Now, this can be any kind of application which runs in Kubernetes. And even better, so to say, you don't even have to restart or rebuild that. So the application actually wouldn't even know that there's a proxy outside that controls that. So that makes it pretty easy for somebody to say, okay, well, I just want to try it out and put that in. And if it's not the right thing for me, I'm going to take it out again. I don't need to rebuild my apps or push new containers or whatsoever. So that makes it pretty easily and accessible. Now, if we look at this diagram again that we had before, so we have our application now running in Kubernetes and thinking of that proxy level, that means basically all of the pods are going to be extended, and that proxy component is being placed inside. And then you have that control plane where each of those proxies would actually connect to. And here you basically see the advantage and the disadvantage. It will be able to collect all the metrics, but it will also have to be everywhere. So not only in a single application, but also in every instance of such an application. And then, yeah, things can get somewhat messy. That's like service mesh is also a term that comes up every now and then. So this is probably where that comes from. Now, but if you look at the possibility side of things, you have now options that you did not have before. So you can say, okay, these are those two applications, and now I have control over those proxies. Now I can certainly say I want to just like secure that traffic between those two components and make sure nothing else can happen. And I'm going to do this with like normal Kubernetes API. Well, I have extended objects like CRDs, but in them I can specify, okay, for example, this traffic will only be allowed to go there if it has a certain source label. It could also do some kind of encryption only on that certain step in between, and it gives you basically control over the network then. Another thing is what we had in the initial slides before, is when I say I want to roll out a new version, and I mean Kubernetes out of the box supports like a kind of a graceful migration from one to another version to make sure this kind of blue-green way works. But it doesn't, out of the box, let you control to say, I want to split the traffic in terms of percentage, or I want to listen on something on the network, like on the network content, either like where it's which region it's coming from, or if certain cookies are set or whatsoever, and then route the traffic based on that. So that's also something that a service mesh will add. In this, and here you see how it's being done. We have like 2 destinations when traffic comes in, and then you can dynamically select what is basically the weight that I want to place here. Now, there's more. So as I said, there is opt-in traffic. You even can do like some fault injection, like going into the direction of chaos engineering, where I say, okay, I want to basically simulate a network outage or a latency, and then see how my application reacts on that. We have circuit breaker retries, security stuff, policy enforcement, and so on. So technically speaking, if you look at something like a gateway would normally do very similar things. So it's not that with the service meshes there is a super new invention, but normally you have one gateway kind of at the entry of your cluster. Now, if you realize you're building more gateways because you need that more often, then something like a service mesh might actually sense. But in turn, it also means that you kind of basically place gateway functionality in every pod, even if it might not be necessary for that particular one at all. So the overhead is definitely higher there. Another side effect, which is of course pretty nice, is now that you have the information of all the traffic in your cluster, you can very easily visualize that. And that might also be helpful for people who are like kind of new to Kubernetes and they just suddenly see how the things flow, who talks to whom, and how those connections work. You can also visualize if you have like this percentage split in traffic like I have here, and we hopefully going to see that in the demo later on as well. It's also good from our own experience to show that to clients. I mean, not every client will understand kubectl output. And I can tell them many times that this is actually doing what it should do. But this is like a diagram of the Spring pet clinic. And this is the output from Kiali on top of Istio. So it looks fairly similar. So you have the gateway, you have the various services, you have the database connections, and so on. So you can actually see if things do what they are supposed to do, and then also get the information about the traffic distribution, the latency, and all those other things. Now, if this is all so great, why does not everybody do it? The problem here is, as I said before, first of all, you have a pretty big overhead because you place that proxy in every pod. So there's going to be overhead in CPU and memory consumption. But probably the even worse thing is the latency that it's going to add. Because if in a previous, like in a way without a service mesh, 2 services would have talked to each other directly, then basically one service talks to the proxy talks to another proxy, and the proxy talks to the app again. So you have multiple hops in there that will not only listen, but also do something with the traffic, and that definitely has an impact. So the CNCF, basically the organization where Kubernetes and all the service meshes belong to, has done this survey in 2021 about the overhead which is getting added by the service meshes. And I don't want to go into the details of at which percentile you kind of get what kind of an overhead. It's just for you to be aware of it before you start with this, that this is definitely going to happen. The other thing, in addition to that, is also that you technically manage another layer. I mean, you have your Kubernetes cluster, you manage the service mesh layer, and the application on top. That means you also need to do the updates and all those things, which can be problematic. Now, what did we see here? So it extends Kubernetes, especially in that shortcomings we saw before about network traffic awareness and traffic shaping. It's pretty easy to inject this sidecar into a pod. It doesn't affect anything else and get a pretty good control there. So yeah, you have the configuration changes at runtime. You don't, not at build time. That's probably one of the important things. All right. Now, one more thing I wanted to talk about is a topic called eBPF. I think when I mentioned this the first time about a year ago, not a lot of people had been using it. But I think the last half year there was a pretty hype cycle around that topic. So who in the room has heard of eBPF? Okay, maybe I can still impress a few then. No, I mean, impress is not the right word. I didn't implement that, but I might be able to tell you something new. Now, this is something which, in a long form, is called the extended Berkeley packet filter. And if you read that twice, it still doesn't sound very much like distributed systems. This is something which is coming from a very low-level Linux side. So if you look at the Linux operating system, there's like a kernel space and a user space. And the kernel space is normally very protected. This is where things shouldn't go wrong. And the user space is normally the one where you can place your applications and run your things. Normally the regular users are not able to do anything in the kernel space. However, it is possible to load some kernel modules and basically run something in the kernel, and this is basically where eBPF comes in. So they have kind of built such a kind of a sandbox mechanism where you can run verified custom code in the kernel space without basically to need to rebuild your kernel and rebuild your operating system. And a simple term that comes along with this explanation very often, like this eBPF in the kernel is somewhat like JavaScript in a browser. So it can run in there, but it shouldn't be able to do any damage to the underlying application or infrastructure. And now, once it runs in there, it can actually listen and interact with kernel events. And network events are such kernel events. So that means for any network traffic that is basically happening, it can intercept that and then basically take that information and forward it to other applications in the user space. I mean, as it is in the kernel, I think everything has to be written in C, and it's fairly complicated to do that. So I think most of the processing would actually happen in the user space, but you have like this handle or trigger, how to say, to interact in a kernel space in a very dynamic way. I mean, the opposite would be that you say, okay, I need this functionality in the kernel, and Linux is open source, and then you need to submit it and merge it and wait for a long time until it finally gets into some release. And this is pretty much like a shortcut how to add functionality there. Now, if you look back at Kubernetes, you probably are aware it's not only running containers, but it itself runs on machines. So they're basically a cluster of machines. So you have mostly virtual machines, and in most cases, they are also Linux machines. So there's an operating system, and then they have the container daemon on top, and various parts that basically make the Kubernetes cluster, like the proxy and the kubelet. But underneath, it's Linux. So that means this eBPF technology will work there as well. So a generic approach how can use that function or use that functionality is basically to say I'm running my eBPF components, like for example in a daemon set, to make sure it's going to be placed on every node with certain privileges that they can execute their code. But then they would be able to query and interact on a Kubernetes level of the node and not on the pods. The control plane idea is pretty similar to what it is with traditional service meshes, but the amount of proxies and the amount of interaction you have is, of course, a lot less. So if in this 4-node cluster example, I would probably have 4 of those proxy agents that would feed into the control plane, and the control plane could interact on those things. So in that approach, the pods are not even touched. There is nothing injected or stopped or started. This is basically something that you normally do beforehand. You can still do it later, but normally you do it in the first place, and then just everything that you run on your cluster will automatically become observable. And yeah, same as with the other service meshes, they extend Kubernetes with own CRDs. So Cilium is a fairly popular example as technology there, and then you can basically put things in there that are similar to a virtual service in Istio, where I say, okay, I'm doing label matching, and only for that input label, I'm gonna route to a target label or to a target port or whatsoever. Everything basically what the network allows. Now this Cilium is fairly young, and they've initially just started of trying to get this as a Kubernetes network handling component in there, and now sorry, they are coming up with a beta program for an own service mesh, like a proxy-free or a sidecar-free service mesh. And for that, they did a survey amongst many users to say, if you build yourself a service mesh or you're thinking about using a service mesh, what would be the most relevant criteria for you to use it? And yeah, it was at least a surprise to me that the number one criteria for a service mesh is not actually interacting with the traffic in any way, but really observing it. So really getting an insight of how things flow is probably the number one thing. And then there are like the other ones, like securing or encrypting the traffic, canary rollouts, rate limiting, circuit breaking, those things we've been talking about before. And I think right at the moment, they are just continue to develop that Cilium service mesh. So observability and encryption is already there. With the other ones, I'm not exactly sure. And this is for like the equivalent graph that you get from Cilium about a Spring pet clinic. Now, to summarize that behavior, it's like you inject that proxy component on the node instead of the pod level. That's basically the bottom line. And with that, you get that low Linux level functionality leveraged for Kubernetes or Kubernetes network behavior, to be pretty precise. This is already, I mean, a lot of people already use that productive. I think a lot of the cloud providers actually already are thinking about putting that into the clusters straight away when they roll them out. And this service mesh is currently in a beta program. So it has lower latency, and because they have less hops as opposed to pod injection, but a certain latency will still be there as well. And I've just seen a recent blog post from Istio. I don't have anything in the slides for that, but Istio has also come up with something now which is called an ambient service mesh with a similar approach to place the proxy nodes in on the worker node instead of the pods. Now, to compare that, to say, so what is better now? Like doing it on a framework basis, using what Kubernetes has, putting the proxies into your pods, or putting into the nodes. I mean, this is most likely a question I cannot answer. It's of course, I'm a consultant, so what would I say? It depends. And it depends. I mean, it depends on the thing that you really need. I mean, I said initially, the first frameworks were like coming from Netflix. Now, not everybody is Netflix, and not everybody has those requirements. So in an approach to make a decision there, I would, for example, say, so which of those functionalities do you actually really need? I mean, do you actually need a Kubernetes and get all those high availability features, or are you never going to make use of them? So this is something I will definitely left unanswered. I'm more like here to outline the various options that you have, and then as a recommendation from my side, especially the ones around Kubernetes, which don't require any change in your code, are pretty easy to try out. So I would recommend to every one of you to just play with it and see how that works for you. So that means we have about 10 minutes left. That was quicker than I thought. I can I can jump in a demo real quick. So what I have is I have two Kubernetes clusters. Both are running that Spring Pet Clinic application. One is on Google, that's the one which is instrumented with Cilium, and one is on Azure, that's the one that's instrumented with Istio. So let me just quickly say, so here is my, so that's the endpoint, and then so right now there is no traffic on it. So I'm going to do the traditional service mesh version first. So as you can see here, is that? So I would have expected it to be a little less, because right now there is no traffic on it, and it stores it for a while. I just did a dry run before the presentation. That's why you can still see the things. But technically, you would have to generate some traffic to see that things are, actually something is going on. So I'm going to take out this URL, and I have this JMeter here. And with that, I can start put some load on the system, and we should be able to. Now it's switched back, and now after a while it should basically pick up again. Now, so it's building up now. What I have actually built in here is for this vet service, I have two different versions. I could do this from command line. I could also enter that right here. And here you would see that virtual service where I can say I have currently a distribution of 50-50. So that should basically be split between the two versions right there. Now we just have to put things in the display. So traffic distribution, we can now see it currently has 66 to 33%. We gotta wait for a while. So now it switches back, so it kind of will level itself out. I mean, the most exciting thing, of course, is the traffic animation, because then things are getting really exciting and beautiful. And you can see that's probably the why so many people pay that overhead. But yeah, I mean, this is things are coming in over this Istio ingress gateway. I can start doing this configuration and adapt that. So no, this was the wrong one. I'm sorry. So I say, well, I'm happy now with that new version, so I'm going to save that and change it to and that should take a couple of seconds, maybe a couple of more seconds until you see the result there. But yeah, so this is basically, and if you look into the cluster, let me just, I'm going to, so this is, for those who don't know, this is K9S. It's like a command line kind of Kubernetes browser. It's just with a wrapper of kubectl, do things like that. And if we look into this namespace called Spring Pet Clinic, you can see here that all of those pods which are running there have this 2 of 2. So looking in there, you basically see you have the actual API gateway, but then you have that Istio proxy. And same here, pretty much everyone has an init container which has already completed, but this proxy and the actual application container will basically run all the time, and hence provide that overhead for you, but also pretty easy to switch them on or off. You can do that for the entire cluster. You can also limit it to certain namespaces. Technically, you could also put it into only individual pods, but that's, I'm not sure if you want to go down that hole. But limiting it to namespaces is probably not a bad thing. All right, then let's have a look at the other cluster. Can you actually read that? Or okay. So that's the one right there. So if we open up that one, then you can see here I have all my pet clinic pods as well. So what was going on there? Okay, then this doesn't look all so good. Well, we'll see. I'm not sure what exactly happened there. We can see in a second. Anyway, what you can already see now that these are single container pods, so nothing has basically been injected there. And let me just see if we can actually get something from the UI. So yeah, it detects all the services. It doesn't detect, I think, the API gateway at the moment. Let me just see if that is running. So the endpoint is here. Yeah, so the application is up. Then it means I can also put, I'm going to stop this one, you have seen that. And I can enter this endpoint for putting some load on. And then, this is the wrong one, too many things are open. Now we should probably see something like an outside access from the world to the API gateway. Now it's getting a bit messed up. It looks nicer if the API gateway basically is put to the left. But anyway, you basically see it goes into all the, that's what I want. It goes into all the details there as well. What we don't see in this graph is like the distribution and the response times, even though Cilium has the technical ability to know that. What I've just found out is that if you want to get those metrics, you have to configure an additional Grafana dashboard where you can actually get those metrics. I didn't do that yet, but it's there, and as I said, they are currently under development of those features, and hopefully they're gonna make their way inside of the application there too. All right, so this one, and as you can see, once the traffic goes away, it kind of collapses again, so it just shows up once things are happening. I have 3 minutes left. I don't know what else I should tell you right now. So first of all, I would like to say thanks for listening. If you like the slides or want to have a look at them, you can take a photo of that QR code and download them from SpeakerDeck. And as I said, if you have any questions, feel free to reach out to me on LinkedIn or Twitter. It's just, I'm not going to stay around long. I have to get back home to my family. So this is probably the better way to find me. But I'll still be here for a few minutes, so if you have any direct questions, please feel free to come. Okay, thanks.